So now we move to another part that now we include the friction into the system. So thinking initially when we try to explain about the work that done to the system, we try to ignore the influence of the frictions. So in this case, if the object moving, so it has some kinetic energy, while the object moving, it has some friction we call the kinetic frictions. This is due to the kinetic friction force here, but thing is different. If you have the isolated system and non-isolated system, the way that a friction involved is different. So I will show you here now. If you are in the isolated system, that means when the object is moving and maybe go through some third part with the friction or resistance, look alike thing that bind together, and it needs some distance with the rough surface. This try to prevent object from the motion, and the direction of the friction is opposite to the direction of object motion. So that if you determine the work that comes from the friction, so when you use force and dot with the displacement, you can see the direction of the force is in the negative side and displacement in positive side. You always have negative Fs. So what is happening here is mean all the chain of kinetic energy. If you have initial velocity and the terminal velocity is stopped, you lost all the kinetic energy to the friction. So in this case, if you have the chain of kinetic energy is due to the friction. However, sometimes you not only have the kinetic energy, sometimes you have the potential energy as well. So total energy change in terms of isolated system that you lost to all of the work that's from the friction. However, if it's in the non-isolated system, that means you have some energy transfer to the system as well. Not only you lost this energy in terms of the kinetic energy and the potential energy, you will lose this to the friction work, right? This is the work done by the friction, and another work as well that other force interact. This is like a U sigma T in a system. So remember, if you have some friction involved, you have to combine into the equation as well. Not only the energy loss, the sharing of energy is due to the work, it's gonna loss due to the friction as well. The negative side is because the friction force is in opposite direction to the displacement. Okay, so now let's look after this problem now. You have the system that you would like to determine the speed of this block after it's moved 3 meters on the surface, and this surface have the friction. So now kinetic friction is not equal to 0. You have the mu k equal to 0.15 in these scenarios. How can you determine the change of the velocities? This one is initially from the rest, so that means the initial velocity is 0. So the work that done to this system, works external, is force with the distance. But with this one has been pulled up by the frictions. So the Fks is the friction, which in this case is delta x, and equal to the change of the kinetics energy. Because it's on the same reference ground, you have no potential energy happen here. This is your first, this is your second. So the change of K you can write as K2 minus K1. So if you deep investigation into this part, this is now non-isolated system, right? If it's non-isolated, you have the external work and you have been reduced by the friction. So the external force that involved here is your F, the pulling this part toward the delta X direction, if I got this as a plus sign. So F delta X is your external work that pulling this object to moving through the friction, which is Fk delta X, and equal to the initial, you have the V initial is 0, so this term is 0. So that got 1/2 mVf squared. So if you're looking after this part, what you have seen here is look like F minus Fk and multiply with delta X. So this is imply you that is your net force or your sigma F here. So that means if you have any force interact in this part, which is you already have 4 force involved, right? But on the normal force and the gravitational force, it's equal. So you get rid of this term, and the force that relevant here is just only in a horizontal F and Fk. So this is your net force, and multiply with distance. This is your external work with friction. So that your final term is only have 1/2 mVf squared. If you would like to determine the Vf, which is, you can rearrange this term in 2/m F minus Fk delta X under the square root. If I sum all the information I know, which is your Fk here, I will rewrite here. Fk is equal to N, right? And you have N that equal to mg here. So you have mg and multiply with mu, because F equal to mu N, right? So this information is for your F. So now you will sum everything in. I will write down at this part square root 2/m, and the mass is 6 kilograms. F minus F, the force that you pulling constantly is 12 newtons, minus mu N, which is 0.15, M, which is 6, and G is 9.8. So I'll state that I will use G equal to 9.8 meter per second square here. So this is your net force in this blanket. This is your net force. And delta X is the displacement that you're moving, is 3, that you pull this object to moving it. Finally, you will find the velocity, which is equal to 1.8, sorry, 1.8 meter per second. This is your velocity. Finally, so let's look after this problem. So since we have the frictions on the ground, so this one is not equal to 0 now, right? And you have the mu k equal to 0.15 as the previous sub question A. So now you like to determine the force that apply angle, sorry. So you'd like to determine the optimum angle, which is when you pull this object with the right angle, you have the maximum potential energy, or maximum kinetic energy, or maximum speed here, right? When you have Vmax, that means you have Kmax as well, because K equal 1 over 2 m Vmax squared, right? The key is try to find the angle that caused the Vmax in this case. So how can you determine it? So let's look at the free body diagram of this object. You write free body diagrams, and you know that with the force applied here, with the direction in parallel to the displacement, because work is F dot S, right? So we determine the force in x direction, which is F cos theta. This is the theta angle. So this is Fy, which is the F sine theta. Not only the force that's pulling, and you can break the components, you will find another force that involved in this part as well. That is the mg and n. Since you have n and F sine theta, so and the mg in balance, so your n may not be the same as mg. When the object pulling on the right handward, so there's some friction happen in the inverse direction of the displacement. So this is the direction, which is the kinetic frictions. This is as the free body diagram that's happened to this box object M, the mass M, sorry. So if you redetermine about the work and energy, so now you would like to look at work and energy theorems. So what is happened in this case? This is now non-isolated system, right? Because you have force pulling this object all the time. If you have the system here, if the system of yourself is just only the box mass M with the friction on the surface, not only the non-isolated system that you will have consider with the friction force as well. So with the friction, that means the change of energy in the system is now the total energy, the transfer, which is in this case you have the external work and you have some friction involved. And D here is your delta X. I will write like this. So now we try to sub all the information that I know into it. So the delta E this system is only the kinetic energy, because in the same planar and the reference position is here, you have no change of the potential energy, the gravitational potential energy. So in this case, you have K2 minus K1 is equal to mu ext minus F delta X. Since your initial position is at rest, here the block initially at rest. So this means your initial velocity is equal to 0. So your K1 is 0. So you would like to determine the angle that have the maximum speed. So you can just rearrange these terms. So you get K2, which is, this is your kinetic energy at this position. This is your K2, is the form of the VF. And what about the external force that you have here is F cos theta, right, with the direction of the delta X. And how about the force F here? As we know, F equal to mu n, right? F equal to mu n. Since your n is the static equilibrium, like you can see sigma Fy equal to 0. Sorry for rewrite this on this part. This is what we only focus on energy already. Now we focus on the sigma y, and sigma y you have n plus f sine theta equal to mg, so that your n is mg minus f sine theta. So now you can sub n into it. So this mu n is mg minus f sine theta, and mu m this is your n, right? This is the f that you have. So delta x is after this. So the delta x is displacement that you have here. So what you get here, you get the f cos theta and minus with mg, mu mg, right? And minus mu f sine theta that multiply with delta x. This is your K2. If you would like to determine the optimum value, the optimum means you have no change when you compare to the specific quantity that you want. Since here the kinetic energy can represent the velocity like this, to find the optimum value, you diff kinetic energy with the angle to find the optimum angle. And this point is like going to be the maximum or the minimum point. So it also depends on the k square over the theta square as well. So now we're going to differentiate this k term and equal to 0, which is what you got. You diff f is a constant, diff size you got cos, diff cos you got the minus sign. So here you got minus f sine theta, right? And all these constant not involved with a theta, so it's all gone. So another term, you got sine here. So finally you get cos afterward. So this is what you get, mu f cos theta. And delta x is like constant. You still have delta x in all these terms. So from this part, also I'm sorry about this one. This is minus, right? If you multiply with this, this is the plus side. This is my problem. So this is the plus side. So finally, when you rearrange this term, you finally get the tan theta equal to all this part is gonna get rid of each other, because f, you can see f is gone. You only have mu equal to tan theta. So in order to find the optimum, theta is equal to arc tan of mu k. This is the optimum theta that you can have the maximum velocities. We don't want to determine the velocity. We would like to determine the optimum values. So if you sub the value of mu k inside to this part, which is 0.15. So finally, you will get theta that equal to 8.5 degrees. And this is how you use the knowledge of the non-isolated system with the friction and try to find the optimum value in this path and use the relation to determine the optimum theta that you pull the object to moving with the maximum velocity.